Okay, and so I've set up all my variables. Okay, and we go to main, and before I go to main, this was regarding how I set up my analog to digital input regarding reading the switches, like the cursor switch, the setting switch, and all that. So I've called it, I've got one switch here, times amps, time, changing the time or changing the amps settings, and it's on the same pin, right? I used one pin, it's going to change voltages. I've got a cursor switch, I've got an analog meter to change the scale on your meter, and I've got one to save the memory, in the program, whatever figure you have set for your time delay or your current reading. But the switches, this was my own idea, what I've worked out. Since I'm reading voltage, I'm using the internal voltage of the chip, which is 4.096 voltage reference built-in microchip with this particular chip. So the voltage can never be higher than 4.09 because that's what your reference is, regardless that you're powering up the chip at 5 volts. And so to make it easier to read, I'm only reading the first 2 digits. Okay, let's say if it's gone 4 volts when you press the switch, 40. Okay, so I'm dividing, when it comes to the calculation, I'm dividing that by 100. So I'm only reading the first 2 digits. So 40 means 4 volts, 26 means 2.6 volts, 22 2.2 volts, and 27 is 2.7. And it's a con, that means it cannot be changed. That variable can never be corrupted. So it's not a variable, it's a constant. So that equals to my switches, that voltage equals to my switches, which switch I have pressed when I work it out. This is the voltage reference of the for the DAC, to read the DAC, and instead of I put 4096 because that's what the voltage reference should be, you actually have physically, manually, okay, get your voltmeter here, measure that point, measure what it is. I've measured it to be 4.090. So in my code, I put 4090. So that's the reason why that is done like that. This is device address. This is in hex, C8. Microchip, for those DACs, they make 4 versions of those chips with different addresses, and that's the versions. So one version has an address of C4, C6, C8, and C8. This particular one that I've used, it's a C8. For talking to the I2C bus, it needs the address, name, number. Okay, I've set up variables here, max amps, and max time, and all that. Now here I'm reading the EEPROM, the built-in EEPROM on the chip, and this was one way to write on different memory locations on the microchip, and this was my idea in how to do it. There's probably better ways. In actual fact, I already know a different way, but this is the way I done it. So it's gonna look for a location ID with a number 0. Once it finds a 0, it's gonna read the next location, and that will be your memory bit numbers that you've saved to whatever variable name. And so I divided the 256 locations by 2 to have half of the memory to store the delay time, and the other half is to store the current limit time in memory. And without going through explaining all this. You can see it there. That's how I've created it. I've used a low byte and a high byte because each location is only a byte. It's not a word. It's only 8-bit. So that's why I've used dot low byte and dot high byte of the same variable to be able to load the variable with an 8-bit number. But Pic Basic Pro, also, you don't have to do it in this way. You can use a different variable name after the different command after your variable, and it does it automatically. It will load up a 2 bytes into a word variable for you by having a different name here, a different command name, okay? Statement. So I'm loading up the memory for the current there, and then here I'm loading up the memory for the time delay from your EEPROM, and so on. That's how it does it there. This is to set up the pulse width modulation of the module inside the microchip, and you would need to read the PDF file, how to do that. And I'm setting up some of the registers here. So the frequency out, which is the pulse width modulation out of the microchip, it's always running in the background. It's not part of the code. It's setting up the variables on the microchip, some special registers that automatically, constantly, just as long as the oscillator is running, you're always going to have the pulse width modulation. So it's quite good. That's the microchip system. And yeah, so by changing the frequency is to change some of these registers when you're changing your settings, and one of your main one will be is this one, PR2, which is the timer 2 period register. Okay. Then I'm doing setting up your LCD screen at the beginning, and that's what this is doing. And last value amps, and your amps value, and last value time, your time value. This is done to stop writing unnecessary writes to the EEPROM, okay? So if you haven't changed your settings, if your last value hasn't changed and you want to save it, you don't need to rewrite into it, because you're going to not damage, but you're actually wearing out bit by bit that location. That's why I made the location each time you write, it jumps to another location, okay? So here's what I've saw with a lot of sketches of Arduino. They don't bother to do that. Sometimes just keeps writing to your EEPROM, even if you haven't changed the value. So, you know, if your door is closed, why go and open it and close it again? You know? So it's a matter of seeing whether it's closed or not. And if you want it closed and it's already closed, don't go and open it and reclosing it. Because every time you write something, that's sort of what you're doing. This has got to do with the interrupts, intcon and all that. So then the code starts over here. On interrupt, go to interrupted. This is the compiler of the system of Pic Basic Pro here. So also regarding the interrupt, because it's going to go to the interrupt, to make the interrupt rotary switch encoder more responsive, I come up with a system here which I have done tests and it actually works. I delay my code once it's gone to an interrupt. So after as soon as you change your rotary switch, it's gone to an interrupt, and then once you stopped, you finish that routine, it comes back to where it was. But because after the return, it's going to return back to here. Because I'm saying if an interrupt flag has been changed to 1, which that's done at the interrupt routine, then I'm delaying here, pauses 1, which is supposed to be 1 microsecond. And the reason why I pause here, because in this case, I am writing, once I've gone to an interrupt, it means I have changed the values of the current reading or the delay time reading. Therefore, you need to talk to the LCD screen to update the figure that you've just changed it to, right? So while it's writing, while it's communicating to the LCD screen, the interrupts are turned off. And the reason why you turn them off, because you want to finish the communication part, is if you, while you're talking, you pulled out, the message is going to be half done, which means it's going to be an error or corruption, or so you don't want that. So once it's writing to the LCD, switch the interrupts off. In most cases, you have to do that if you don't want any errors on your LCD screen. So because of that, right, if you, while it's writing to the screen, your rotary switch, when you change it, if it's talking to the screen, it means it's not going to be going to an interrupt because you switch the interrupts off. Yes. So since I am doing that, what I do is I pause the code in this loop. I do a for loop here. Okay. And to wait to see if you're still turning the rotary encoder. Yes. And after a certain delay time, if you're not turning the rotary encoder, right? Well, nothing to do with if you're turning the encoder, but after this delay time, then it's going to do and either talking to your LCD screen or talking to the deck to write to the deck. Because again, while writing to the deck, you're using the I2C. Therefore, you don't want the interrupts on, because otherwise it could not talk properly to your deck and give it the full message to change the voltage level, which means you've set the current reading of your deck to be a different number. Well, I mean different voltage, of course. The interrupts are turned off. So if I'm happening to turn the switch, the rotary switch, I'm delaying here for 1 microsecond, and if it needs to go to another interrupt because I'm still turning the switch, the code's not having gone to the I2C writing. So this program loop, I come up with it with my own experiments and practice. I haven't seen this anywhere on the internet. I think that a lot of people would not know you could do that. Okay, so that's something I'm sharing there. People that do programming might know what I'm talking about here. Okay, so that's what it's doing. So main, and after if you went to an interrupt, of course you will do this loop here, this if statement. If you haven't been to an interrupt, you don't do this. So if I've gone to the interrupt and changed the figures regarding the amps settings, this is an error regarding my deck. It's to try to correct the output voltage. Okay, so I'm doing some calculations here. Okay, that's how I've done it. I'm not going to explain it. It's going to take too long. Once you do your adjustment for your deck, then it writes to the deck. Okay, and then it says go to deck formula, deck formula. I'll go to that just to show you. Okay, that is here. And this, of course, I've got from the PDF file of the deck. Decimal number to convert, to get your decimal number from your voltage and from your bits. You do this formula, and you see here I have to use that divide by 32. If I was using C, you wouldn't write it like this. You will do it in a much easier way. Here you have to create a dummy 32-bit because the number is going to be bigger than a 16-bit number, and therefore you have to do it in this way. Here's where it becomes complicated under Pic Basic Pro. And once you've done your calculation, then load up your decimal number into the bits of the deck. It's using the 3rd byte and the 4th byte. That's regarding the register bytes of the MCP4725. And people of Arduino use the same system here. Okay, it's pretty much written pretty much in the same way. That's the quickest sort of way you could do it, by shifting the bits. Okay, go back here to your main. We're going to loop for 1 second in a for loop, reading the current. So this is to set the which reference you want to use, the analog to digital converter, which is first I'm starting off with the 1.024, and that can read pretty much up to 1 volt. Okay, and after just a bit higher than 1 volt, I change to the 2.048 voltage reference. Okay, if it's higher than that, we'll change to the 2nd reference, and I do the amps calculation there. Okay, what's this? Okay, what I did here, you don't have to put this in actual fact, I might take it off. If current is greater than amps by 50%, if you set your delay time for 1 second, okay, which is 1000 milliseconds, if the current is higher more than 50%, if you set it to read half an amp, let's say 500 milliamps, and the current has gone to 1 amps, which is double, so let's say 50% more than what you've set, I've made the delay time settings go from 1 second to whatever you had it goes to 1 millisecond. So that's what that does. Okay, I don't have to have that because now I've got an overload circuit. So if there's a short circuit, for example, now I've got a different op-amp to trigger an SCR, which I explained in my hardware here. If there's an overload, it's going to trigger this SCR regardless if this MOSFET is on, off or on. Okay, so I don't really need this anymore. So originally I never had the SCR and the op-amp in the circuit board. So this is like my 2nd circuit board that I did, okay? And the first one I used to do that. I used to, because, you know, if just in case there's a short circuit, it's going to wait for 1 second. If you set it to 1 second, that you might blow up your SCR or your equipment, you know, whatever you're doing. So, and again, this is not a very good way because it's relying on the software. Where if you do it in the hardware actions regarding sensing, it's better than having the software to do it in a way for speed. Once the hardware senses it, it's going to be much quicker than your software. There's always delay times in software. So yes, so that's what that was. And again, because Pic Basic is complicated to the maths, I had to look how to work out 50%. Now if you're doing writing in C, I'm not sure how you would do that in C, but I know it would be simpler than this. So look what I had to do. To work out 50%, if amps is greater than temp amps, okay, this is a temporary variable, times 5 divided by 10 plus the temp amps. Let's just get the 50%. And flag limit, of course. Then time value equals 1. Okay, now if you could see that, yep. And then I say go sub time limit, and that's so you go and change your time figure. Okay, so that's what that is. So after 1 second, that for loop will end, next loop, okay? And while it's looping in the for loop for 1 second, okay, you're going to read the switches to see if you've pressed the switch. Okay, so that's done there. Read switches. And that's done here. Read set switches, okay? And that's your label. And just in case your reference is not the correct one, I change the register here, which in fact I don't think I have to do that because I'm actually I'd have to check. Anyway, add sim command, which is pin 9, that's the ADCs to read your switches, and I'm putting that variable, the voltage, on ADC switch. Okay, I've got actually a timer running here, timer +1, and that was done. So when you hold down the cursor switch for 3 seconds, it will show you the internal on the LCD screen, the internal variable regarding the pulse width modulation registers. So that's why that was done. Here I'm finding out if cursor and scale switch are pressed, save the new values. That's to see if you press 2 buttons together, the voltage will be different. That's to go and save your different figures. And here I used a select case statement to be able to work out which switch you have pressed. So if the select case ADC switch, that's where you stored your voltage when you pressed one of the switches. And if it was case 30, and 30 was the 3 second delay time. So once 3 seconds that switch been held down for, put the number 30, which thinks like it's as if it's 3 volts, into the ADC switch. And you do this section, which means service. It means it's going to display your internal values. And it does your code there. And if it was the cursor switch, it will does the cursor or moves your cursor, goes up step cursor. That means the switch was 2.1 something volts. I'm not sure if that's correct now, but if it was the analog meter switch, it means it was around 2.5. And it changes your scale, relays, it's done there. And if it was your time or amp settings, it means it would read 4 volts because 4.09, so it's 4 volts because it's divided by 100. And it sets your variable whether you are changing the amps or whether you're going to change your time. So that's what that does there. And returns. And after 1 second, when because I'm pausing pause 1, which is 1 millisecond, by the for loop time, which is 1000. It's probably slightly a bit more than 1 second, okay? Because you gotta really allow the timing of the lines here, the statements. And then after 1 second, we'll read the voltage, okay? And the voltage, I'm reading it in 3 steps. Originally I didn't have that, so when I showed the videos of the doing the testing, if those people that look at detail, you would have noticed that I wasn't using this, but because if you look at the first digits, it was jumping by 4. Let's say 20.3 volts, or you couldn't really get the 3 because it's jumping by 4. That is because I only used the 4.096, but later I've changed it to this, and that's why I'm showing this again now. I'm changing the video to show this. I only used the 4.096 voltage reference, so now I'm starting off with the 1.023 or 1.024 voltage reference, so I can read up to let's say 102 volts, and then it will changes to the 2.048, and once it reaches that, then I change to the 4096. Okay, so I'm getting more accurate lower voltage. Okay, so that's,
and here also, right, it's something I like to mention again. I don't know if the Arduino people do it now, but from the sketches that I have seen, I never see people do this statement here. What this statement is going to do is going to check, okay? You're going to display something on the LCD screen, right? So I'm explaining this for the people that are learning, for the benefit of those people to learn something maybe new, or they might know it. Is if you are reading voltage, and for example you are reading 4 volts, the analog to digital converter have read 4 volts. If the value have not changed, so it's still 4 volts, you've read it again, and you're reading it here in this command, right? In Arduino will be in a different section how you read it. If the last value that you read when you went to read it, you store that last value in a variable. Now you read it again. So you're going to test whether that last value has changed. So I've got amps, for example, and I've got voltage, right? Let's say I'm reading voltage. So I've got 2 variables, one called old volts. That means the last value. You can call it last value, last volts instead of old, okay? I called it old. You're going to compare it. So here's the comparison, and this is the same in C. Compilers, the 2 arrows like that. If volts is not equal, that's what that does, to old volts. That means if it's not the same, right, then old volts equals volts. So now, if it was 4 volts, the last value, and the new value is 3 volts. So that means this if statement is going to be correct because it's not the same. It compared them together, comparison. Then save the 3 volts into the old volts because the old volts had 4 volts before. So now we put 3 volts in the old volts. And now I'm allowing, I've got a flag here, LCD flag equals 1. Okay? I'm allowing what this flag means when it comes to talk to the I2C to the LCD screen. I'm allowing it to rewrite the LCD screen to display the new number. Now, I have seen a lot of sketches getting back. I'm taking long to explain this. So, if the value have not changed, why are you going to write on your LCD? You shouldn't do that. Why is that? Because every time you do a write, first of all, in most codes, if you're using interrupts, you have to switch off the interrupt. That means you delaying your interrupt now, because if you happen to turn your rotary code encoder, which means it should jump to an interrupt. Because I'm writing to the screen, it cannot go to the interrupt. You can make it go to the interrupt, but then get prepared for your LCD screen to display some error. Okay? Because you never left the communication to finish. So you only update, okay? You only update your screen if the values have changed. If they haven't changed, no need to update them because it's going to be the same. So you're wasting time and delaying your code to run if you don't use these. So as practice, I have learned, and I've learned this on my own, by the way, because no one ever explained this. I haven't seen anybody explaining it. So hopefully I'll be one of the first person to explain this on a video. So yes, that's what I have learned. That's what I would advise. If always check and compare your values. If when you write to something, you know, that's like saying, can someone please close the door? The same person, I'm going to keep sending him to close the door when the door has not been opened. It's still closed. So why am I sending the person to close the door again? I'm wasting time. I'm wasting people's time. I'm wasting the code time, which could be interfering with jumping to an interrupt, for example, in this situation. Okay, moving on. I'm calculating the watts to display it on the LCD screen, so you need to times the volts by amps, and because the number could be bigger than a 32-bit, 16-bit, then I have to use this stupid divide by 32 command, and I have to create a dummy 32-bit to be able to hold that number and to be able to do my calculation, just in case it's bigger than a word. Again, with Arduino you don't have that problem. With C professional programs you don't have that problem. Okay, if your LCD flag is a 1, which means now something has changed because I have changed it, now you can write to your LCD screen. And these are using Daryl Taylor's include file, and this LCD write buff, it's like a statement he created under assembly. Okay. And those people that run Pic Basic Pro would know what this is, and that's how you write to your LCD screen. So that's the display, by the way, the internal service. So in normal situation I don't show that. So when I'm showing the current and your voltage is here, and I'm displaying your amps, I'm displaying the voltage, I'm displaying the power, and so that's that. Okay. You need to show the cursor every time you write to the LCD screen, and I'm reading the switches again to make it more responsive there, and I am updating your analog meter scale because this has auto scale. And that's why I'm going go sub analog meter. I've created a label there, and let's go to that analog meter, and here it is. And what this does, I'm using a if statements in this case here. This is how the relays of the voltmeter. So getting back. Here is my scales. Okay. Here is my relays for the scale to change the current transformer tapping through the relays. Okay. And the microcontroller is turning off and on one of these relays. Okay. Automatically, depending on what the current is. Going back to that,
and depending on what the current is, so if meter scale equals 3, that depends which settings you're in, how many times you press the button. Could be, if you press it 3 times, then it counts 3, so it knows which section you're in. And if the current is over, for example, 2.5, then change your scale to the times 5. So, and it does it here. Switch off your if meter, yes, it's testing to see if the meter is already in 5 or not. If 5 is not on, turn it on. Then delay for 60 milliseconds. And here I'm using a delay before I turn off your other relays, whichever it is, and I'm not testing for whichever it is for the reason that I'm not sure if these are on, off or on, just to make sure I want them all off. But 60 milliseconds after I've turned on a different relay. And you remember when I explained to why that is, and I'm going to re-explain it here, is because I don't want to break the circuit. Let's say I have the load on, okay? Let's say the load here is on, and I'm changing to a different scale, okay, of your analog meter, okay? If I wanted to go to the 5 amp, or let's say the software have realized that it was on the 2.5 and the current went higher than 2.5, therefore now the scale, the needle is hit the stopper, and it cannot go anymore. You know, there's no more scale to show. You need to change the scale to a higher, to the 5 amps is the next setup. Next step up is the 5 amp scale. So first turn on the 5 amp scale, and at 60 milliseconds after, turn off the 2.5 scale, okay? Or if you were on a different scale, you turned it off 60 milliseconds after. Stopping, so not stopping, that will ensure that you haven't broke your circuit, which means if you don't have that delay and you switch the relay 2.5 off, when the 5 amp meets, it's going to arc because your load is on, and you're going to damage your contacts on the relay. So that's again the explanation behind that. Okay, so adjusting that. So this what it does. This is the auto changing, how I've made it. And I had to have 2 systems because one is for one scale. When it's done the times 1, your values here are different. And when it is divided by 10, I have to change these figures. So then, else, if it's on the different scale, then I'm dividing it by 10. You see the figures have a 0 missing there, the first digit. Okay, go back to the main. So we did that. This shows your display whether the circuit breaker is on or whether it's been tripped. Okay, and again I've got a flag, and the flag, trip flag. Once it displayed power is on, that means the circuit breaker is on and it's not tripped. You don't want it to keep writing to the LCD screen. The same thing that I explained before. So I've created a trip flag. So once you showed power on, set your trip flag to 1. If it's been tripped, it means it come here, and the trip flag, set it to 0. So once it's tripped, okay, the trip flag needs to be 1 again to display, to do this loop.
So I'm not writing to the unnecessary, talking to the LCD screen for nothing. So that's why it's written in that way. Again, I haven't seen people in Arduino doing that. Okay. This checks for your switch, the ×2 switch. It's done there. Here's my interrupt routine. That means the rotary encoder have been turned. An interrupt has been sensed. This is my own system, okay? I come up with this many years ago when I used to try to work it out how to do this, how to read a rotary encoder. And depending on which rotary encoder you're using, this system might have to change here. And I've done it in this way. Actual state, and the rotary state is actually done in port B, which is reading the last, I'm going to read the last 2 bits, 6 and 7 of port B, and I'm shifting 6, and then I'm left with the last 2 bits, 6 and 7, okay, of port B. And then I'm going to load those last 2 bits in the variable called ACT state, actual state. You probably can use better names than what I did. So then here I'm working out, am I changing the time or am I changing the amps? Because the button is one button, and the set value, that means what you're going to display on your LCD screen, is one variable. The reason why I used one, to make the code quicker in your interrupt. But I need to know which one am I going to load onto that set value. Is it a time or is it the amps? So that's what that does there. And then I'm going to check whether to see if the rotary encoder have been turned clockwise or anti-clockwise. And it does it here. So the actual state, if it's 1 and it's 0, it means it's gone clockwise. And the last state needs to be 1, 1. And the last state on this particular rotary encoder that I've used, in between the notches of the clicks of your rotary switch, in between is always a 1, 1. That means the 2 pins coming out of the rotary switch is a high. Okay, those bits are 1, 1. It means I have crossed the middle section of the switch. I'm jumping by 1 there. So if that matches and that matches, okay, to stop errors, I wanted to know that. Then it's clockwise. If it's this 0 and 1, sorry, 6 and 7, or the bits of the rotary encoder is a 0 and a 1 this time, it means it's going anti-clockwise. Okay? So this tells you to go to that label clockwise and anti-clockwise. So the anti-clockwise I do if set value is greater or equals to the multiplier. And the reason of the multiplier, I'm counting by 1 in normal situation if you're on the first digit. But if you are on a second digit, depending where your cursor is, you might want to times it, plus it by 10 or plus it by 100. So it means the multiplier is going to tell you that. And that is in your cursor section. Here's your multiplier, step cursor amps. So depending on where the cursor is showing on your LCD screen, it could be, the multiplier could be 1000, could be a 100, could be a 10, or could be a 1. That means the first digit, let's say 3000 milliamps here, right?
don't worry about that. That's actually should be 1000, because after 1000 I change scales. But anyway, the 1, multiplier 1, is the first digit here, the last 0. The 10 is the second digit. The 100 is the third digit, and the 1000 is the first digit. So that's what that is. So value, so set the set value plus the multiplier. If the value is bigger, larger than the max value, which in the beginning of the code I've set a max number, okay, then the value will have to equal to max value. The set value, make it equal to the max value. Then as soon as you changed it, you updated the value, you need to display it on your LCD screen. Otherwise you're turning your rotary encoder, but your eyes are concentrating on your LCD screen. So you need to update the LCD screen as soon as you change the value. That's what you have to do it in steps. And you know, the step is watching your eyes onto the LCD. So you need to update it. Goes up rotary LCD, rotary LCD, and it's down here. Anyway, it's there. Now this is a bit not complex, but because of my scaling, I've got two scales here. One is a ×1, the other one is divided by 10. If your scale is ×1, which means your scale pin will be a 0. That's not the actual scale pin, but it's another round figure out variable I've used, which corresponds to the scale pin. If the amps value is greater than 1.1 amps, that's what that number is, I'm going to change to the second scale. So the amps value needs to be divided by 10, because I've changed the scale. And the max value needs to be divided by 10 as well. So set scale equals 1, scale pin equals 1. Now I'm going to change to the divide by 10, which means I have to change the scale. So when you're reading current now, going back to the circuit, so your software is always corresponding to what the hardware is, or to change your hardware. So when we go back to the circuit, now I have turned on the divide by 10, the 100 ohm in total, okay, of your scale of the toroidal transformer here. So now the voltage here is going to be divided by 10. And I'm turning on this MOSFET here. Go back to the code. That's what that's doing. The scale pin is the actual hardware output out of the microchip to turn on the MOSFET on, which means divides the voltage by 10 of the current reading. Then goes up step the cursor, amps, change scale, flag equals 1. That means I've got a flag there called change scale. I am pausing in this case 300 milliseconds to give enough time. Since the voltage would have been higher being on the ×1, and now I'm dividing it by 10, the hardware needs to settle down. Reason why that was done, for anybody that is interested in this, is because if your load is on, if your load is off, you don't have to put this. Why is that? Because your current's going to be 0. That means the voltage is going to be 0 millivolts. And therefore you don't need to settle the voltage, because it's already settled to 0, right? But if your load is on,
if it was reading, for example now, right, let's say if it was reading 1 volt, which stands for 1 amp under the times 1, now it's going to be divided by 10, so now it's going to be 100 millivolts. The circuit, because I've got the RC networks to filter the AC to DC and smoothing out, there's going to be a delay before that can settle down to the right correct voltage. If I don't put the delay here and your circuit is on, it might trip the circuit breaker, because suddenly now I haven't updated the DAC, right? So the DAC's still reading a certain voltage, and now I've just changed the voltage, so it means that it could trip. And then if it's smaller than 1.1 amps, okay, then you need to times it by 10. That's the else. So if it's the scale is not a 0, if it's a 1 else, then obviously you're already in the divide by 10. That's where this software is a bit complicated, because you got to keep in mind what your hardware is doing. That means that because I've got a divide by 10 hardware, the 1.1 amp will be 110 then times it by 10, okay, because it means I'm going to change scales. It's a bit hard to understand, but that anyway, this works, and that's how I have to do it. And then if I'm going up, you need to write to the DAC straight away. So in this case, I don't have to go to the main in the beginning if I've changed after the interrupt. Before I go to the main, I'm actually updating the DAC first. Otherwise, if I come down with the current, it's going to trip. Okay, so depending on what scale you're changing to. So update it straight away, the DAC, and then once you change the DAC, then change your scale. You see here, set scale to 0, set scale to the pin to 0. That means I've changed from divide by 10 to 1 times 1, which means the voltage is going to be higher. So I had to update the DAC first, since the DAC determines when your trip point is. Okay, and the trip section is not done through the software, it's done through the hardware. I have to make sure the DAC is updated first, then change your scale. Okay, so that's why it's done like that there. When you're doing your time, changing the time delay, what are you going to set 800 milliseconds after the trip point? You come to this label here, and you're going to do the statements here, which I've called rotary time. This is the way I've done it here. It might be improved if people you know, have more experience than me, but it was quite a bit of complex thing to do to change the frequency of the pulse width modulation, and this is the way I've done it. I had to use the pre-scaler to be able to, once it hit a certain level, I couldn't go anymore, I couldn't change the frequency, so then I had to change the pre-scaler. So I'm using the sorry, what am I doing there? Sorry, I'm telling you wrong here. The pre-scaler is done by TM2, timer 2, which is actually here, T2 con, okay, is times 1, times 4, times 16, times 64. They're the settings in the pre-scaler. And this corresponds to what your frequency needs to be, okay? So then I've set if it's larger than 16, the time value, let's say 16 obviously milliseconds, then you change the prescaler to the next one, 16. If it's bigger than 65, you change it to the 64. You change it to 16. I'm lying, I'm jumping wrong. If it's greater than 260, it's when you change to 64. And this sets your time, the T2 con, to be able to get that 64, okay, a prescaler, so you change the figure there. And I've wrote here T set timer 2 con to prescaler of 64. Okay. And again, to work out the formula, divide the time value by 1 to 8 of the 440 counter pin. And it's done in this way, sort of done backwards. And that's how I had to do it, okay? I had to work that out. And then to display the, to work out your PR2 from whatever time value you have set, you have to do pulse width modulation period equals PR2 plus 1. This is in the PDF file, by the way, of microchip. Times 4, times TOSC, timer oscillator, times timer 2 prescaler value. Okay, and that will change your frequency period, which is the frequency. So by reversing the formula, okay, which I did here, I can work out what PR2 needs to be for whatever time value I needed. Okay, and then there's an example here, what frequency I need, how to work it out. Then this is done to get microseconds. Yes. Yes, I think this is based on, let's see, frequency oscillator. 0.25, okay, yeah, that's 0.25, but I'm running it under rate, so yeah, it's 125. And for the 8 megahertz, that's what the period is. And that's how I've calculated it. Variable microseconds. What have I done here? This was a while ago that I've done this, probably a year ago. This is to show your frequency when you're showing your display, the service display. So you don't actually need all this, but this is to show it on the LCD screen if you want. The main part is already done because it's what PR2 is. And then you display it on your LCD screen here. And depending if it's times 2, instead of doing it in the calculation, I leave the calculation the same. So I'm still using the 1 to 8. That means Q8 of the CD4040. And when I'm timesing the value by 2 to read off the 256, I didn't redo the calculation in 256. No point. All I had to do is times it by 2 on the LCD screen. And that's what I did. I'm timesing whether it's the scale is on times 1 or times 2. I just display it times 2 on your LCD screen. And I don't have to alter the formula in the code, just to make it simpler. So that's why I did that. Okay, something that I haven't really showed on the Variac project is the output of the frequency out from the Pic chip. So what I did, I hooked up an oscilloscope on the pin and I'm showing the frequency. If you can see here, it's saying it's 41.67 kilohertz. And if you read my display here, mine is in hertz, 41666. Of course, I do not really like that last 3666, as if it's the number of the beast, but it happens to be in the calculation here. And you can see PR2 equals to 48, and also my time, it's saying in the bottom 3 milliseconds, 0.003 seconds. The period time equals to 24 microseconds, as you can see there. And also on the oscilloscope it's saying 24 microseconds. So now if I change the frequency by turning the dial here, so I'm on the 10th second digit. Now I've got 13 seconds, and as you can see, my frequency here, it's saying 9.90 kilohertz or 9900 hertz, and the oscilloscope it's reading 9.8 kilohertz. So very close, right? Also my period is 101 microseconds, and you can see here it's changing from 101.6 microseconds to 102 microseconds for the period. Okay, so we'll see how that is worked out. So we got 0.013 seconds, so 13 milliseconds. So we got a calculator, we do 13 milliseconds, I'm working in milliseconds, times, sorry, I'm doing it wrong. We're gonna use the period, okay, which is 101 microseconds, right? So milliseconds will be 0.101 times 128 for the CD4040, which is on pin 128, which is on the 128 count, equals to 12.928 milliseconds, and I've got 13 milliseconds. So that's what I've set the time. Okay, so that's as close as I can get with the formula. Remember, depending on the resolution of the pulse width modulation timing on the module, the resolution, I can't get full each resolution every 1 millisecond. I cannot. So again, I changed the frequency here, and you should see the frequency change. Okay, now I'm on 23 milliseconds. Okay, just to show you. Okay, I'm changing the milliseconds, and I'm changing, and then you can see the frequency changing. So the oscilloscope is saying 892 hertz, 892.9, and if you look at my display, it's saying 892 hertz, and the microseconds is 1120 microseconds for the period, or 1.120 milliseconds. And if you look at what the oscilloscope saying, is 1.120 milliseconds. So now the bottom display, it's saying I've got 143 milliseconds I set for the trip time. So let's see if we can get that figure. So we'll do 1.2, sorry, start again, 1.120, okay, milliseconds times 128. 143. Okay, 0.36 milliseconds. And what does my display says? 0.143 seconds, 143 milliseconds. Okay, so you can see that that corresponds to that. Now if I go to the highest reading that I can go, which is 1.048 seconds. Okay, the frequency on the oscilloscope is 122 hertz. Okay, you can see there. And if you look at the frequency on my LCD display, it's saying 122 hertz. Okay, and this is saying the period is 8.2 milliseconds, and I've got 8192 microseconds on my calculation, or 8.192 milliseconds. So if you use, again with the calculator, 8.192 milliseconds times 128, right, will give us 1048 milliseconds, which equals to 1.048 milliseconds. And my display says 1.048 seconds. So it's correct. So you can see that the calculation I did in the program equates to pretty much the real thing. Okay. Save amps. Set EEPROM values if changed from the last saved value. Okay. The first byte is the location ID, which has to be 0, as I explained. Then it's the 2 bytes for saved value. Is this the first location after the ID, and the second location will be put into the saved value figure. Okay. It should be, that's what should be there. And as I explained, that was to help the RAM longevity. Using all RAM is important by shuffling forward the RAM for saving values, okay? Because of frequent saving in EEPROM, every time you change values, this must be done. You don't have to do it. In the past, I never used to do it, but because this type of project is gonna, since you're gonna change values all the time for your different settings, you are constantly writing to the EEPROM. Not constantly, every time you change the values. And if you decide to go over all the cursor steps, then it will save the value. And we save the values here. So you need to read the last value saved. If the last value is equals, not equals, I mean, to the new value, then the last value equals amps, right? So if the values have not changed, we're not going to write to the EEPROM. We're only going to write to the EEPROM if the value is different to the last saved value into the EEPROM. Okay, so I'll give sort of like a basic explanation here. How I'm writing it. EEPROM location equals the location start write A. That means I'm going to write to the amps location. So we need to know where the location is for the next locations on the EEPROM to write. We're going to go through a for loop here. Actually, sorry, that's not a for loop, it's an if statement. If end of EEPROM start, okay, so I've reached the end 128 location, then start again at location 0. Now the EEPROM location equals 2. I didn't put a 0. This is 2, not a 0. as below it minus 2, which becomes 0, okay? So, because I'm always have to step, every time you write to the new location, you have to erase, which I'm writing again, the last 2 locations, actually last 3 locations, because the first location is the ID location, okay? So, because I'm always have to go back, I had to put a 2 there, because it will become a 0 here. Set value equals the amps value. If set scale, now depending on your scale, as I said, it's going to affect, do you need to divide it by, times it by 10 or divide it by 10, or if it's not times 10, then it's already been divided, okay? So, if the set scale is 1, then set value equals set value times 10. And I had to do this because then when the program, when you switch off the machine and you put it back on, it's going to read the location on the EEPROM to put it into the set value. I was getting the value being as if it was divided by 10, so I had to times it by 10. The right location, first here we're going to erase first, and then we're going to write. So the location start for the amps equals EEPROM location minus 2. So we're going to erase here, write location with FF. That's what the default values normally are on the EEPROM. Okay? Then the location start A equals location start A plus 1. I have to jump and rewrite the second location. Okay? And then put a 0, okay? After you plus it again, I moved, because it's locked back to front now. When you're reading it, it's reading it sort of from left to right, and in this section here as if I went from right to left. And then the start location is a 0, and that's done for the ID. Write ID with a 0. So the names here could be confusing, like why am I still using that, but I've already changed position. This is just a location number on the EEPROM. Bit complicated to explain, that's unfortunately that's how it is. EEPROM location amps equals location start, okay, plus 1. So again now, because I was at the ID, I had to jump to the next location, count 1 up next to location, ready for actual values, okay? Because after the ID, which is a 0, I told it there, then is the actual first byte and then the second byte, okay? So from 0 I got a plus 1 for the location, and I'm going to write now. I'm going to write the first byte of the location into the location, I should say. Write EEPROM location amps, right, which is being changed there, telling it which location it is, and put the first byte, so the low byte of the set value of the amps. Then once you've written that, you need to write the high byte, so the location needs to plus 1, next location is the current saved value, okay? And here we're going to write again the second byte into the EEPROM location and write it with the high byte of the set value. That's because it's a 16-bit number, right? So I have a low byte and a high byte. And then go sub display saved value, because the code, once it writes to it, it displays on your LCD screen that you have saved the value. And
if we go display save value, where is that? Display save value is here, and it's going to tell us new value saved. It's going to display that on the LCD screen. That's all that does. And here, to force regarding of what the LCD flag was set at, I'm toggling the trip flag as well, okay, and the LCD flag equals 1, okay. So, and when you save the time, it's the same system as what I just explained for saving the current. So saving the time is the same way. You need to work out, have the value from the last value have been changed. If it's not, if it didn't change, you jump over that and you return, okay? If the value of the time has not been changed, then we're going to write to the time, and you do the same thing. If it's greater 255, which is now you hit the highest location number, and we're going to display EEPROM time override. We're going to go back and we're going to start again from the beginning of the locations of the time. And I don't know if I and same thing, I didn't explain that. And same thing with the amps. Once you go over 128, it's going to go back to 0, okay? So it displays it on the LCD screen. That's so I would know that, geez, I've used the whole locations, and now it's going to rewrite again from the beginning, okay? You don't need to have that in place. So that's it. And thank you for watching. Sorry for my mistakes. I have made a lot of errors in my speech. Could have said the wrong words, which I'll try to put some text when I re-edit the video, okay? Well, in this case, the video would have been already edited and you should have saw those. Yeah, so my apologies.